Okay, so now that we talked about the first law of thermodynamics, we talked about our equation, delta E is equal to Q plus W. We talked about Q, we talked about W. Let's talk about two different situations that occur with the first law. So one is where we're going to keep the volume of the system constant, and then the second where we're keeping the pressure of the system constant. So let's try the first system out. Now, keep in mind that the first law says this, that change in internal energy is equal to Q plus W. But what we learned in the last video was that work, if we define this in terms of chemistry instead of physical definition, work is equal to negative P delta V. So what I'm going to do is replace the W term in the first law equation with negative P delta V. Okay, so if I pop that value in, I get that the change in internal energy is equal to Q minus P delta V. All right, so here it is. So what I'm saying in this situation where we're keeping the volume constant, delta V is going to be 0. All right, so if delta V is 0, that means P times delta V is also going to be 0. So this whole term drops out. So we get that delta E, the change in internal energy, is going to be equal to heat, Q. Now to show that we're keeping the volume constant, next to this Q in the subscript, we're going to write Q sub V, and that tells us that the V is that the volume is being kept constant. Okay, so that's pretty easy. If we're keeping the volume constant, that whole term, negative P delta V, drops out because V ends up being 0. And so then when we're measuring the change in internal energy, that's going to just be equal to the heat at constant volume. Okay. Drawback of all this, though, is that it's extremely difficult and near impossible to keep a reaction going under constant volume. It's possible, but it's very unlikely. Not a normal chemical reaction that we would do. Okay, so just keep that in mind. It's going to be near impossible for us to replicate that, but it can be done. Now here, what about the second way of doing this? Okay, now what if we keep the pressure constant? Okay, so before I do that, I've got to introduce a new term, or two scenarios. So let's say you've got a reaction that results in a net increase in the number of moles of a gas. Then that means that the system does work on the surroundings, and we call this expansion. All right. Now, if there's a net decrease in the number of moles, so the reaction consumes more moles than it produces, then that means that work is being done on the system by the surroundings. So the system is essentially kind of contracting. Now, if there is no net change, then that means no work is being done. So keep in mind this. I'm going to explain this in a little bit, why we want to keep this in mind. But if we have a constant pressure process, so let me write the first law again, delta E, change in internal energy is equal to Q plus W, but we know that work is equal to negative P delta V, so we're going to replace W with negative P delta V. So we get that delta E is equal to Q minus P delta V. All right, so what I'm saying now is that P is kept constant. Well, looking at this equation, P is already constant. It's not changing. So P is already constant. Well, so what do we do with that? So what I'm going to do is I'm going to make sure that to indicate that we're holding pressure constant. I'm going to go up to the Q, and then in subscript, just like they did for the last time by writing a V, I'm going to put a P. So that indicates that the reaction is held, that the reaction is being held with pressure constant. One final thing I'm going to do is rearrange this equation. What if we solve for Q? Okay, in order to have Q by itself, we have to add both sides. We have to add P delta V to both sides. So we get that Q at constant pressure would be equal to delta E plus P delta V. Okay, now keep that in mind because I'm going to introduce a new term that we call enthalpy. So enthalpy, which is represented as capital H, is defined by the equation enthalpy H is equal to internal energy, E, plus PV. Wait a minute. That looks really similar to what we just wrote earlier. And here's the reason. Remember that E, in changing the internal energy, P, pressure, volume, these are all state functions. So if E, P, and V are all state functions, that means that H also has to be a state function. So if the pressure is held constant, we can take this equation here and rewrite it as this. Delta H, the change in enthalpy, is equal to delta E, the change in internal energy, plus P delta V. Okay. Now, here's that equation that we looked at previously. That was the heat at constant pressure. So Q sub P is equal to delta E plus P delta V. But wait a minute. That's the same thing. The only difference is the front part, delta H and Q. So that means, to conclude, since these two are the same, that the right-hand sides are the same, that the heat at constant pressure has to be equal to the change in enthalpy. And so at heat at constant pressure, when we hold pressure constant, we talk about the change in enthalpy instead of the change in internal energy. Enthalpy is a much, much widely used term instead of delta E. So we talk about delta H instead of delta E. So the enthalpy of a reaction is the difference between the enthalpies of the products and the enthalpies of the reactants, or saying this, that the change in enthalpy for the reaction is equal to the enthalpies of the products minus the enthalpies of the reactants. Okay. Now, delta H can be positive or negative. So if delta H is positive, then that means that Q also has to be positive. And so that indicates an endothermic process. Okay, and likewise, if delta H is negative, that means heat has to be negative, and this indicates exothermic. All right, last topic. There's got to be a way to relate delta E and delta H to all this. Now, it turns out that both values are roughly equivalent to each other, but delta H values are usually just a hair smaller than delta E values. And this is due to some of the internal energy being used to do gas expansion work, so that means less heat is evolved. All right, so remember that to calculate delta H, we write this, that delta H is equal to delta E plus P delta V. Okay. Now, to solve for delta E, we would have to rearrange these equations. We'd have to subtract P delta V from both sides, and we would get this, that delta E would be equal to delta H minus P delta V. Okay. Now, we can also express the internal energy in terms of the number of moles of a reaction. Now, keep in mind that we talked about the ideal gas law in the last chapter, that the ideal gas law says this, PV equals nRT. Now, in order to take that, use that into account, we've got this term that says P delta V. So what I'm going to do is, instead of writing P delta V, I'm going to rewrite it as this, delta PV instead of P delta V. All right, so here's what we got. So the equation that we have is delta E is equal to delta H minus P delta V. Okay, so that's what we have. So I'm going to rewrite that equation by keeping in mind that we've got the change of PV. So delta E is equal to delta H minus delta, and then in parentheses PV. Now, if I apply the ideal gas law to this, I can swap out PV with nRT. So we get this, that delta E is equal to delta H minus delta nRT. All right, cool. So here's the problem, though. R is a constant. We talked about that. And anytime we're doing a thermochemical reaction, we're keeping temperature constant. So R and T are constants. Because of that, we can move them out of this description and put it before the delta sign. So we would get this, that delta E is equal to delta H minus RT delta N. And so going back to before what we were talking about, delta N, this is the change in the number of moles. So this is going to be the number of gas moles of product minus the number of gas moles of reactants. And so that's how internal energy and delta H are related to each other.